This figure shows the plan view of a piezometer and a well field consisting of 4 pumping wells in a flat area. Each well has its own volume flux or discharge Q and circle of influence large R. The drawdown at distances small r from a specific well can be calculated by inserting the right values for Q, small r, and large R in the Dupuy equation. We may rewrite the Dupuy equation as shown here. S is the drawdown H minus H large R. Remember, a pumping well has a positive discharge and a recharge well has a negative discharge. Therefore, S is a negative number for a pumping well and a positive number for a recharge well. There is no regional groundwater flow. The piezometer measures the hydraulic head as influenced by all 4 pumping wells. The principle of superposition applies, that is, the total drawdown, S total in meters, at any location within the circles of influence of the wells can be calculated as the sum of the drawdowns of each well. Thus, S total equals S1 plus S2 plus S3 plus S4. If the location of the piezometer lies outside the area of influence of a specific well, then of course there is no drawdown effect from this specific well discernible at the location of the piezometer. Probably needless to say that in case of a recharge well in this well field, its contribution is not a lowering of the hydraulic head, but an increase of the hydraulic head, and that its contribution should be treated accordingly. In this figure there are 4 pumping wells, and the hydraulic head H in the piezometer after steady conditions have set in can be found by summation of the pre-pumping hydraulic head H large R and the total drawdown S total at the location of the piezometer. This figure shows streamlines in plan view and the potentiometric surface in cross-section for a recharge well and pumping well. A recharge well and pumping well, let us decide from west to east. There is no regional groundwater flow, and the total drawdown S total can, similar to the procedure just outlined, be established by adding together S1 caused by the recharge well, S1 is positive, and S2 caused by the pumping well, S2 is negative. Interestingly, this causes a constant hydraulic head equal to the pre-pumping hydraulic head H large R exactly at the midpoint between both wells, as can be seen in this cross-section. From the plan view, it is clear that this midpoint is part of a line with a constant hydraulic head equal to the pre-pumping hydraulic head H large R, and that this line extends in a north-south direction perpendicular to the cross-section. Now imagine a situation with a pumping well and to the left, west of it, open water, a lake or canal, with a straight right eastern boundary coinciding with the line with constant hydraulic head H large R just mentioned. In reality, as the open water and groundwater meet at this straight boundary, and because the open water is continuously replenished from upstream, the water level at the open water boundary would remain at this constant level H large R all the time, before pumping and also after pumping commenced. In fact, if one had wanted to insert an open water linear boundary in one's groundwater flow model with a constant hydraulic head H large R to the left or west of the pumping well, mirroring the pumping well, to the other side of the open water linear boundary, converting it into a recharge well with the same absolute volume flux, thus Q1 equals minus Q2, and then adding S1 and S2 together to give S total would just have been the way to go about it. The mirrored well is called an image well. In reality, this well does not exist, but is solely incorporated into the model for the wanted effect of creating an open water linear boundary with constant hydraulic head H large R to the left or west of the pumping well. The part of the model that exists in reality is the part to the right, to the east of this open water linear boundary. A known constant hydraulic head at the boundary of a water flow region is called a Dirichlet boundary condition, after German mathematician Johann Peter Gustav Lejeune Dirichlet. If now we have a piezometer located at XY, a pumping well indicated as a real well here, and a river modeled as an open water linear boundary with to the left or west of it water, then we can determine the drawdown at the piezometer by using the principle of superposition. We add together the drawdown due to the real pumping well at R1 and the increase in hydraulic head due to the image recharge well at R2 to determine the real drawdown at the location of the piezometer with a real pumping well and a real river border near to it. Pumping groundwater from a sandy aquifer bordering a river, the situation just modeled, to provide for drinking water has as major advantages that the groundwater is abundantly replenished from its connection with the surface water, plus that the surface water contribution that moves as groundwater through the sandy subsoil, if this takes, as a rule of thumb, at least some 60 days, is biologically purified and freed from disease-causing microorganisms. Pumping groundwater from an aquifer bordering a river is a technique much used alongside major rivers in Germany. Similarly, this figure shows streamlines in plan view and the potentiometric surface in cross-section, west, east again, between two wells, but now both wells are pumping wells that have equal volume fluxes or discharges, thus Q1 equals Q2. It is clear from the cross-section that this setup creates a flat potentiometric surface at the midpoint and midline between both wells. This flat potentiometric surface is obtained by adding this surface and this surface together. A flat potentiometric surface means no hydraulic gradient and thus no groundwater flow at the midline between both wells, and thus the creation of a no-flow linear boundary. A known constant volume flux at the boundary of a water flow region is called a Neumann boundary condition, after German mathematician Carl Gottfried Neumann. Thus, in this particular case, the Neumann boundary condition is a constant volume flux of 0. This figure summarizes how to calculate the drawdown at a location in the vicinity of a pumping well near A, an open water linear boundary, and B, a no-flow linear boundary, an impermeable area. One should first mirror the pumping well, indicated with a small circle as just explained, calculate the drawdown, negative value, using the distance R2 to the pumping well, then calculate the drawdown, positive or negative, using the distance R1 to the image well, Here the image well is indicated with a cross, it's a recharge well, and here with a circular symbol, it's a pumping well. And then, of course, apply the principle of superposition by adding these two drawdowns together to give the total drawdown as total. Had the original or real well been a recharge well instead of a pumping well, then modeling an open water linear boundary would have involved the creation of an image pumping well, and modeling a no-flow linear boundary would then have involved the creation of an image recharge well.